I'm Astrid Olave, and today I want to talk generalizing the interleaving distance using categorical flows. Let's start with an example. Let's take two modules, f and g, persistent modules. They are assignments from the real numbers to modules or vector spaces. Here we have them generated by these elements, and I want to compare them. Maybe I cannot do it one-to-one, but I can do some shift to do it. Let me explain. So I can go from sigma to 0 and then go back to this generator. But I would like to have some commutativity. So I want to go from sigma to sigma here from left to right. And I would like to have the same if I go down and up. And here is not the case. If I go from sigma to 0, then I don't have a way back to sigma. So one step is not good. What if I try a two-step? Now this looks better, right? From sigma, I can go to epsilon, and then I can assign it to sigma again, and I have the commutativity that I was talking of. But if I want to have this relationship between these two, I want to do it for all the possible arrows. Like this, up and down, these two, and so on. So the idea is for any epsilon, we say that f and g are epsilon interleaved if there is a pair of natural transformations, phi and c, such that for all a that belong to the real line, the diagrams commute. So these two being natural transformations means these parallelograms commute. So going down and right is the same as right and down. And this is the triangle that I was talking before. Like going up and down is the same as going from left to right. And if you notice, we cannot find any epsilon to make this f and g interleave. If I choose sigma to go to 0, I have no way back to go to sigma. And if I choose sigma to go to epsilon and go back to sigma, when I try to do it with tau, goes back to epsilon and then goes to sigma. So choosing one makes the commutativity of the other to not be true. And well, this continues forever. So those are the only possible assignments that we have here on the bottom. So if we have this notion of being interleaved, we can put a distance. We define the interleaving distance between the modules f and g by the infimum of those epsilons such that the modules are epsilon interleaved. In our case, there's no epsilon such that that's true, so it means the interleaving distance is equal to infinity. So now I want to redefine my terms using categorical language. This was done in 2004 by Bubenic and Scott. They redeveloped all this topological persistence from a categorical point of view. So now we see a persistence model as a functor that goes from the real numbers or opposite to the vector space or any category. And we still want this 4 to hold, to have this commutativity, but we want to write them in categorical way, so we need to add new elements. This shift of b that takes a to a plus b, and this natural transformation that tells me that this shift it preserves the order on the real numbers. So a is smaller than a plus b. And we can use these two elements to encode exactly these two forms, two diagrams that I was telling you before. We would like to use categories because it opens a new world for persistence models. Now we can choose any poset that the functor starts from and go to virtually any category. Some examples, we can do zigzag posets, we can do multi-parameter posets like Rn, or start with a lattice. And this is whole theory about persistence, topology, or homology on those posets. And we have some restrictions on the categories. They have to be essentially small symmetric monadic categories or by complete or Grothendieck categories. Good news is the examples that we usually use, like finite sets, vector spaces, abelian groups, finite abelian groups, and so on, they are like that, so we are good to go. So categories are nice to use. But if you recall, the interleaving distance was between functors. What if I wanted to do it to objects? So between objects. And this was done in 2018 by De Silva, Monge, and Stefanu, generalizing interleavings defining categorical flows. So do you recall this definition that I told you before, these new elements? We can use them to generalize interleavings in any category. So we define an action we call T, that's basically a functor from the real numbers, or from 0 to infinity to be more precise, to the, let's call them actions in the category. So for each epsilon, I'm assigning an action of epsilon, a transformation inside the category. And now we have new pair of elements. Maybe the zero action is not the same as the identity, so we need an arrow to connect them. And the composition between the action of zeta and epsilon is not the same as the action of epsilon plus zeta, so we need to put an arrow here as well. And if we have this kind of T defined, then we have a flow on the category. Let's do an example. This is gonna make it more clear. Let's use the slide category of real value functions that go from any topological space X to R. We note it as this pair. And we're gonna define a flow. So let's take this read graph. Probably I'm gonna call it bacteria from now on. It looks like a bacteria. And where epsilon action is taking the bacteria and thickening. How we thickening? We do the Cartesian product with minus epsilon to epsilon. And now the function that of f goes to f epsilon that takes the value on the point and then adds the value on the interval. So here exactly, if I, let's say, a step right here, it will be the point and then add the interval, so it will be exactly 1. If I do it again, if I do the epsilon action again, it's like double thickening. So in this case, I'm doing it from left to right to give this 3D representation. And now the value will be going up and left or right, depending on your interval. So if you see, now we need this natural transformation that I was telling you before. It's not the same to do a double thickening as doing a thickening by 2 epsilon, but we can connect them with an arrow. I can step to a point and going up and right is the same as going up and up. So here we have our definition of T epsilon, we have our natural transformation, and you can see it's easy to see that this bacteria with thickening 0 is the same as itself. It's just the Cartesian product with the singleton 0, which is isomorphic. So now we have defined a flow into this category. What is an interleaving distance here? So let's try to do the interleaving between this bacteria and a circle. If we have an interleaving from before, I would like to have a transformation or a morphism that goes to the thickening circle and then goes back to the thickening by 2 epsilon of the bacteria, and the same on the other way around. But now we don't have access to this morphism. Not like this. We need to do something like this. We need to add up the other double thickening that we had before. So now our interleaving distance comes this way. We say that these two are weakly epsilon interleaved if there is a family of morphisms, phi and C, such that the diagrams commute. Now these diagrams have 5 arrows. We go from the bacteria to the thickening circle, to the double thickening of the bacteria, and then we use natural transformation to go, oh, that's a different epsilon. Oh, well, to the thickening by 2 epsilon of the bacteria. And the other path is going to the 0 thickening and then to the thickening by 2 epsilon. So the interleaving has, instead of a triangle, this diagram, this pentagon, you can say it that way. And the parallelogram we had before is related with T being well defined as a function. And that's a weakly interleaving. And naturally, we can define the distance between 2 objects as the infimum, such that the 2 objects are weakly epsilon interleaved. So now we have successfully defined an interleaving between objects. Formally, it looks like this. In our particular case, and let's imagine these spaces were actually homeomorphic, the interleaving distance on this category induced by the flow coincides with the L infinity distance for real value functions. That is, for any f and g, the interleaving distance between these two is the same as the L infinity, where here phi corresponds to homeomorphisms between x and y. And it's kind of easy to prove. Like you can check that a phi that is doing the interleaving here induces homeomorphisms, and then homeomorphism here induces a pair of morphisms to do the weakly interleaving distance, or weakly epsilon interleaving, sorry. So that's great news. Interleaving distance appear in other contexts, not only as a theoretical aspects. And here are more examples. We can define this interleaving distance using flows between phylogenetic trees. It's called cophonetic distance. Distance between Reef graphs and labeled Reef graphs. The Hausdorff distance itself is an interleaving distance. We can think about thickenings of the set and see when one is contained on the other, and distance between mapper graphs, something that I'm working on generalizing the idea. And that's all what I want to say. If you have more questions, you can contact me in the email from the first slides. Thank you.